Introduction. Aman, can you please come here? I want to ask you something. What happened today? See there. A machine is moving the scrap of iron and steel from the waste material. Yes, I can see that. But how is it possible to extract the desired material from the wastage? It is simple. Basically, it is an electromagnetic crane which works on the principle of magnetism. Its anchor is made up of an electromagnet. When electric current is passed through it, it behaves like a magnet and attracts only iron and steel from the scrap. Okay, I got the answer of my question, and I want to know more about this. Will you please tell me? Sure. Today we will study about the magnetism and matter.
Objectives.
At the end of this lesson, you'll be able to define magnetism and bar magnet, know about magnetic field lines, analyze bar magnet as an equivalent solenoid, analyze dipole in a uniform magnetic field, describe Gauss's law in magnetism, know about Earth's magnetism, define magnetization and magnetic intensity, understand magnetic properties of material, analyze hysteresis curve, describe permanent magnets and electromagnet. Definition. The phenomenon of attracting magnetic substances like iron, nickel, cobalt, etc. is called magnetism. A body possessing the property of magnetism is called magnet. The two centers of attraction in any magnet are called its poles and are named as North Pole and South Pole. The region around a magnet in which it exerts forces on other magnets and on objects made of iron is called a magnetic field. Bar magnet. A magnet in the form of a bar with magnetic poles at each end is known as a bar magnet. The main properties of a bar magnet are as follows. When a magnet is suspended freely, it aligns itself with one end pointing towards north of Earth and other towards south of Earth. Unlike poles attract and like poles repel each other. A magnet attracts magnetic materials. This attraction is maximum at the poles. Isolated magnetic pole does not exist. Magnetic poles always exist in pairs. A magnet can induce magnetism in substances like soft iron, cobalt, nickel, and various ferrous alloys. Magnetic field lines. A magnetic field can be represented by lines called the magnetic field lines. A magnetic field line is defined as the curve, the tangent to which at any point gives the direction of the magnetic field at that point. Magnetic field lines never intersect each other. The magnetic field is stronger in regions where the field lines are relatively close together and weaker where they are relatively far apart. Magnetic field lines are always closed continuous loops. Bar magnet as an equivalent solenoid. The magnetic field patterns are similar of solenoid and bar magnet. Also, the solenoid itself behaves as a bar magnet with the north pole on one side and the south pole on the other side. Two adjacent solenoids can be either attracted to or repelled from each other, depending on the relative directions of the currents. Let us consider a solenoid of length 2L and radius R composed of a series of n current loops, each carrying a current I. The magnitude of magnetic field at an axial point P due to this elemental loop is given by mu naught upon 4 pi multiplied by 2m upon r cube, when m is the magnetic moment of solenoid. This is exactly the same as that of a bar magnet at far-off axial point. Assessment. Before proceeding further, let us know how much have you learned. Drag and drop the correct option. Dipole in an uniform magnetic field. We consider a bar magnet of pole strength Qm and length 2L placed at an angle theta with a uniform magnetic field B. The forces exerted by magnetic field on the two poles are equal and opposite so that they form a couple. Torque is equal to force into lever arm. By putting the values in the above equation, we get the value of torque equals to mb sine theta. Vectorially, it is represented as tau is equal to cross product of m and b. This is exactly the same as that of a current-carrying coil in a magnetic field. Potential energy of the magnetic dipole with dipole moment M in the field B is given by negative dot product of M and B. Example. Let's take an example of dipole in a uniform magnetic field. A short bar magnet of magnetic moment 0.40 joule per Tesla is placed with its axis at an angle of 30 degrees with a uniform external magnetic field of 0.16 Tesla. Find the magnitude of the torque exerted on the magnet by the field. Let's see the solution. Here given values are: M is equal to 0.40 joule per Tesla, theta is equal to 30 degrees, B is equal to 0.16 Tesla. We know that tau is equal to cross product of M and B, or in terms of magnitude, tau is equal to mb sine theta. Put the values in the above equation. Tau is equal to 0.40 into 0.16 into sine 30 degrees. On calculating the equation, we get the value of tau, which is equal to 0.032 joules. Hence, torque exerted on the magnet by the field is equal to 0.032 joules. Gauss's law in magnetism. Magnetic flux. It is a measure of the number of magnetic field lines cutting through a hypothetical surface in a magnetic field. If a loop of wire enclosing a planar area A is placed in a uniform magnetic field B, then the magnetic flux phi B through the loop is given by dot product of B and A, which is equal to BA cos theta, where theta is the angle between magnetic field and the normal to the plane of the loop. For an arbitrary closed surface immersed in a general magnetic field, the magnetic flux is defined as an integral over the surface. Phi B is equal to closed integral of B dot dA. Gauss's law of magnetism states that the net magnetic flux through a closed surface is always zero. Closed integral of B dot dA is equal to 0. The SI unit of magnetic flux is Weber. Earth's magnetism. The magnetic field at the surface of the Earth varies from 0.3 G to 0.6 G. The straight line passing through the magnetic north and south poles of the Earth is called its magnetic axis. The geographic and magnetic axes of the Earth are inclined at an angle of about 11.3 degrees. The possible source of the Earth's magnetic field is charge-carrying convection current in the outer, liquid part of the Earth's core. This phenomenon is known as dynamo effect. The magnetic meridian at a place is the vertical plane passing through the place and the magnetic axis. The great circle on the Earth's surface perpendicular to the magnetic axis is the magnetic equator. Declination, alpha. The angle between the geographical meridian and magnetic meridian at a place is called the magnetic declination at that place. Angle of dip, delta. The angle between the Earth's magnetic field and the horizontal direction at a place is called the angle of dip at that place. The angle of dip is 0 at the magnetic equator and 90 degrees at the magnetic poles. Horizontal component of Earth's magnetic field, BH. It is the component of the Earth's magnetic field in the horizontal direction. Tan delta is equal to BV divided by BH. We can also write this equation as B is equal to under root of BH square plus BV square. Magnetization and magnetic intensity. The magnetic state of a bulk piece of material is characterized by its magnetization, which is defined as the magnetic dipole moment per unit volume. The magnetization depends on both the magnitude of the individual atomic dipole moments and their degree of alignment. Magnetic field intensity. It is defined as the ratio of the magnetic field in free space to the permeability of the free space. H is equal to B naught divided by mu naught. The magnetic intensity depends on the geometry of the circuit and the conduction current, but not on the medium. The total magnetic field in a magnetic material is due to the conduction current in the external circuit and the microscopic current developed in the material. B is equal to B naught plus mu naught M. It can also be written as B is equal to mu naught multiplied by H plus M. The magnetic field is also called the magnetic flux density or the magnetic induction. The magnetic susceptibility of a material is defined as the ratio of M to H. It is a measure of how susceptible a material is to being magnetized when placed in an external field of intensity H. M is equal to product of Xi and H. Magnetic properties of material. Materials can be divided broadly into the following three categories: diamagnetic substances, paramagnetic substances, ferromagnetic substances. Diamagnetic substances. Diamagnetic substances are those which are feebly repelled by magnets and tend to move from high to low magnetic field region. The individual atoms do not possess any net magnetic moment on their own. The magnetization M varies with H in a linear way. M is equal to Xi H. The magnetic susceptibility is a small negative number and is independent of temperature. The relative permeability is slightly less than 1. The superconductors exhibit perfect diamagnetism. The phenomenon of perfect diamagnetism in superconductors is called the Meissner effect. Paramagnetic substances. Paramagnetic substances are those which are feebly attracted by magnets and tend to move from low to high magnetic field region. The individual atoms possess permanent magnetic dipole moment. The susceptibility is a small positive number and it is inversely proportional to the absolute temperature. Xi is equal to C upon T. The relative permeability is slightly greater than 1. Ferromagnetic substances. Ferromagnetic substances are those which are strongly attracted by magnets and tend to move from high to low magnetic field region. Atoms have permanent magnetic dipole moments which are spontaneously organized into domains of uniform magnetization. M is not directly proportional to H. The susceptibility is positive and very large, but no longer constant. Xi is equal to C upon T minus Tc. The relative permeability is much greater than 1. Two effects may occur when a ferromagnetic material is placed in an external magnetic field: rotation of the domains so that they become more closely aligned with external field, increase in the size of those domains that are already aligned with the field. Hysteresis curve. We consider a ferromagnetic material inserted in a solenoid. Initially, both H and B are 0. We increase H by increasing the current. The magnetization and hence B increases to its saturated value as shown by the segment AB. We now decrease H to 0. B does not retrace its original path but follows the path BC. The value of B at point C when H is equal to 0 is called retentivity. If we reverse the current, we reach the point D at which B is equal to 0. The value of H at point D when B is equal to 0 is called coercivity. As we further increase the reversed current, B saturates in the opposite direction at point E and turning the current to 0 at point F. If we increase the current, B again gets saturated value at point B. The path BCDEFGB can be repeatedly followed. The closed curve BCDEFGB, which represents a cycle of magnetization of a ferromagnetic material, is called its hysteresis loop. Hard ferromagnetic materials have large coercivity and are characterized by broad hysteresis loop. These materials are used to make permanent magnets. Soft ferromagnetic materials have small coercivity and are characterized by narrow hysteresis loop. They dissipate less energy when they are cycled through a hysteresis loop. They are used in devices such as transformers, permanent magnets, and electromagnet. Materials which retain their ferromagnetic property for a long period of time are called permanent magnets. For making permanent magnets, materials are selected which have high retentivity so that the magnet is strong and high coercivity. For example, steel, alnico, and cobalt steel. Solenoids are often referred to as electromagnets. Frequently, ferromagnetic materials, which have high permeability and low retentivity, are placed inside a solenoid to make strong electromagnets. Electromagnets are used in electric bells, loudspeakers, telephone diagrams, magnetic resonance imaging, MRI, cranes to lift heavy materials. Electromagnets have several advantages over permanent magnets. The north and south poles of an electromagnet can be readily switched by reversing the current. The strength of the magnetic field can be altered by changing the current or the number of turns per unit length. Did you know? The Earth's magnetic field is not constant in time. It has been found that the direction of the Earth's magnetic field has been reversed several times during the last million years. Magnets can be used to decrease the white cell blood count, which increases in most diseases. Birds are able to find their way home by using the Earth's magnetic field to guide them on long-distance flights. Summary. Let us summarize what we have learned. The region around a magnet in which it exerts force on other magnets and on objects made of iron is called a magnetic field. A magnet is in the form of a bar with magnetic poles at each end is known as bar magnet. A magnetic field line is defined as the curve, the tangent to which at any point gives the direction of the magnetic field at that point. Gauss's law for magnetism states that the net magnetic flux through a closed surface is always zero. The possible source of the Earth's magnetic field is charge-carrying convection current in the outer, liquid part of the Earth's core and is known as dynamo effect. The magnetization depends on both the magnitude of the individual atomic dipole moments and their degree of alignment. Magnetic field is defined as the ratio of the magnetic field in free surface to the permeability of the free surface. The angle between the geographical meridian and magnetic meridian at a place is called the magnetic declination at that place. The closed curve, which represents a cycle of magnetization of a ferromagnetic material, is called its hysteresis loop.